Now we will build our Q table algorithm code. So we will just build the whole thing. So as a main loop for our code, and here we start by having we will loop into the episode in range of the episodes we don't need this one, just keep it like this, and episode of what we already defined here, the number of episodes, which is 35,000 35,000 episodes. So in range of episode, or 0 to episode, this one. And what we will do is we will start the game. So every one episode we will have steps that is corresponding to an actual game, and after we finish we will rerun, reset our environment, and we play the game again. So we start our work by discrete state equals environment dot reset. So here we put the state, which is the temperature in our case, and then we reset it again. Inf.reset, reset, what will return to us? It will return state. And what is the state? Is the initial temperature. So here discrete state equals equals the reset of the environment, and of course it will reset the length of the environment. So here we also put done equals false, and that means what we will do is, again, we will play one game. So the game will keep on going until we have a signal of done equals false, or done equals true. That means we rerun to another state. So here we said if we have the length become 0 or less than 0, we will have a done equals true that will be returned from the step method. So here we will do if episode the remainder of the of this of episode divided by every episode is become 0. So basically every 5,000 steps, what we will do, we will print the episode. So it's just, we say, like, we will print the number of episode every time we reach 5,000. So of course you can do whatever you want, like you can say like current episode equals this one, while not done. What will happen? We will keep playing. So the reason we put while statement, of course you can say from 0 to 60, it's also gonna work if you define, but of course you can, because we have the signal that the game is done, we have this done thing, or the control length is done, we have the done thing. If you want to define the length from this area, then go ahead, you just write for in range of 0 to 60, for example. So until basically you will go 60 steps. In our case, we just use done here. So if we continue, and if np random So the game starts in here. We reset the environment, and now what we will do is we need the epsilon greedy thing. So if we generate a random number, of course between 0 and 1, and if that number become more than epsilon, what will happen? We will go, the action will be greedy. np.argmax, the q table, we have the discrete state. So argmax is a function that tells us where is the ID of the of an array that has the maximum value. So in our case, we pass on the Q table for that state. So one row, we took one row, and argmax is going to see that that list, and will take the highest number at that list ID. It will take the ID, so it will say that it will have 0, 1, or 2 in our case. So, and it will store it here as this is the greedy location. What if we don't have this condition? So else, basically take random. Action equals np random between 0 and 2, of course. Random dot rand integer between 0 and environment dot action space, or action underscore space dot n, and this is basically is how long the how many action space we have. So this is from 0, it will be 3 here, but so again the way that Python will work will take 0, 1, or 2, and will not take 3. This will return the number 3, and this way of coding is a little bit more robust than, of course, writing 3 here. Of course, you can also write 3, but it's better to use the env.actionspace.n as, because we passed on the environment here. So it's better to write it like this, because you can change the environment, you can change your actions and so on. In our case, you can change the actions from increasing 1 degree, you can increase it to half degree. And so you will have 5 actions: increase 1 degree, increase half degree, do nothing, increase decrease half degree, and decrease 1 degree. You can also do that. New state, reward, and done. This is whatever else, we just take it, but in our case info, but we're not interested. We just put it in here. That means we know there are many others, but we will take the first 3. Well, inf dot step, and action. So we pass on the action, which is here, and into the step function, and which it will work to give us state, new state, a new reward, and the done condition, and of course info. So here, what we will say, well, basically, this one, once we assign it the discrete state, or we can call it new discrete state, because we will use it to calculate the Q matrix. This is going to be, the current state will be here. The discrete, or the current state is will be calculated, and we will already have the current state, and then the new state we will have it in here because we updated the things. And now what we will do is, if we need to just print out what happened here, episode, also reminder, basically this one, just take it here, print Now we will say the episode. We want to print the episode. And we want to print the action or epsilon. So we need to epsilon. Where is epsilon? Epsilon. So again, this epsilon will be changed with time. So episode and epsilon. And we need to have the new state, this value. So after taking the action, where did we, what state we are? And then we want to also say the action. Of course, from action and new state, we can calculate the current state. And just get it up a little. And we need also reward. So how much reward we got? We pass step. Oh. This is reward. And with that we will print what's happening, and then if not done, we need to calculate. If we're not done, what we will calculate is we're going to calculate the Q value, and we will update the Q matrix. So the maximum feature of Q equals np dot max and Q table, this one basically. But we need to pass, this is the new state. So this is going to be, in the Parman equation, is going to be the next maximum state. The current Q is going to be also the Q table, but this state, which is our current state, because until now we didn't update, we start here, we then found the new updated state. Now we will calculate, and then this state has to be like, we have to update it because this is means that our current state. We will take the current state and the current Q of the action we have. So number one, number two, whatever the action is, we have it. Now the new Q value will equals 1 minus, sorry, 1 minus learning rate. This is, we just directly apply Parman equation. Where is the learning rate? Learning rate. This is just application of Parman equation multiplied by the current Q plus learning rate multiplied, of course, again, this is just direct application of Kalman equation. Reward plus discount multiplied by the maximum feature. So we just calculate Kalman equation, or this part of the code will calculate the Kalman equation. Make it a bit beautiful here. Yeah. Just okay. Okay, maybe like this. Learning rate plus this. Or just put like this. Yeah. Anyway. So we literally calculate the Kalman equation. And then what we need to do, we need to update the Q learning. So Q table for our current state and the action we take will equals simply the new Q value. Also, after this, what we will need to do is the current value will equal, it's better to call it actually current, will equal to the new value. Now, by this, we already finished playing the game. However, there are one thing we didn't do, which is the epsilon. So every episode, we will decay our epsilon. So if episode is more than or equal, you remember we set here the start epsilon decay. If it's more than this value, what will happen? Epsilon will equal epsilon multiplied by epsilon decay value. We take the epsilon decay value. So if it's not, we didn't get to 5,000, nothing will happen. Once we get to 5,000, the decay will start to happen. After that, we close the environment. And of course, we didn't define the method of close. Again, it is defined from the from passing the environment of gem. And this way, I hope will run without problems. And it's running now, of course. Now we see at first at the current epsilon state, episode number 0, we start the game is played, and here it's the game is played completely random because epsilon is 1 in here. The epsilon is 1 means we are doing random. You can see like he's getting mostly minus 1 sometimes is there, but yeah, most of the time is actually not so good. So here we can, after 5,000, still epsilon is 1, nothing, everything is like kind of random. Now once we get 10,000, epsilon become less, and of course there are some actions are taken random and some actions are taken not random. 15,000, it's getting better. You can see many 1 many he's getting rewards, and of course one here 20,000, 25,000, 30,000, he's doing very well. Sometimes he go like 23, he went down, he directly took a good action. And basically this is how our Q table is learning. Now if you want to see our Q table, so we can print out our Q table. So this is the updated Q table. Now you can see here still many like random numbers, but here you can see it's a very nice kind of solid numbers because most of our updates are getting into this location. As always, he's trying to go into the location of our control values. So if you want to do also, like, we can print the location of our control. So of course Q table, but we will print Q table in the location between 23 and 28. So 23 is the temperature will be 23, 24, 25, 26, and 27. 28 we will not print it because again this is how Python. So 23, 24, 25, 26, 27, and 27 he will take action number 0, which we say it's minus. He's reducing the temperature. And action 3 is, we said it's plus 1, it will increase the temperature 1. So you can see here, if he got into 27, he will reduce the temperature by 1, and if he got into 23, he will not take the first action minus 1 or 0, he will take increase by 1